All right, let's do this. First things first, let's find the area of this parallelogram looking thing here. Of each parallelogram. So here's the parallelogram. Well, we have the base, and we know the area is just base times height. So the area is just 8 times whatever the height is. So all we have to do is find the height, which is in a 30, 60, 90 triangle. And so that's similar to 30, 60, 90, 1, root 3, 2. And so over here we have to go, well, what piece is in that triangle? Well, if the rectangle here is 5 by height, then this is 5, right? I mean, it shows that it's marked there. And so we get that that's 5. That means this is 3. So what we did is we multiplied by 3. So that means the height is 3, root 3. So we go back over here, and that's 3, root 3. So the overall is 24 root 3 for the area. It's just saying area. Okay, so we got 24 root 3. Smash that into a calculator. Okay, the next one. Same thing, except it's a 45, 45, 90 triangle. So if that's 7, we go, that's similar to my 45, 45, 90, 1, 1, root 2. We don't have an easy what we multiplied by, so we'll just set up a proportion, and we'll say, well, we want to know what x is, right? It's the same thing here and here. And so we say, okay, shoot, what's that? Oh, and it even tells us that that's the same as this. That's handy. So here's an x here too. Or I guess I'll put it on the bottom so we can see it. All right, so let's just solve for it. So x is to 1, right? Going this direction. X is to 1 as 7 is to root 2. Oh, well, x over 1 is just, x over 1 is x, so we have x already. It's 7 over root 2. So we'll simplify when we get to our answer. I'll leave it like that for now. So what we have is area of a parallelogram is base times height. So the base is 2 of the, whoa, I wrote 7. I meant 7. 2 times 7 over root 2. That's the base, because there's 2 of those. And then the height is 1 of them. So times 7 over root 2. Oh, well, look at that. If we multiply these, I'll leave the 2 out for now. And 7 over root 2 times 7 over root 2 is 49 over 2. And then times 2, that's just 49. So the area of this is exactly 49. Hey, that worked out nicely. I like that. Okay. Down here we have find the area of this figure, okay? So you could either see it as a big piece and take things away, or chop it into these. So I'm going to see it like this. Okay, whoa, look at all those equal things. So we have 5 and 2.4, and if you look at this up here, we have this piece is congruent to this, and this, and this, and this, and it spans the 5. So we have 5 congruent pieces, so each of those is 1. And that's a 1 there too, a 1 and 1. And then this one's 2.4, it says it's congruent. So we have the area of the total is the area of the big rectangle, plus the area of the medium rectangle, plus the area of the little teeny one. And so they're all base times height. So the bottom one is 5 times 2.4. The next one is 2.4 times 1. And the next one is 1 times 1. So we have, that's what? Whoa, that's, I'm trying to do math in my head and it's not working right now. Sorry. I think this is 14, right? I'm going to have to pull out my calculator. My brain is not doing arithmetic right now. I've been doing too many problems. Okay, 5 times 2.4, 12. That makes more sense because it's not point. Yeah, okay. Anyways, plus 2.4 plus 1. Okay, so that's 14. 16.4 plus 1, or 17.4. All right, classify quadrilateral with vertices there and there. List all that apply. Okay, so let's do it over here. So we have vertices at 1, 2, 3, 4, 1. Got it. At 8, so that's 1, 2, 3, 4 more, and down -2. Okay, so 8, -2. We have 0, -2. And we have 4, negative 5. So 1, 2, 3, 4, down 3, and down 1, 2, 3 more. That's 4, negative 5, and this is 4, 1. Okay, so first things first, I see two easy things that we can check. I mean, we have a horizontal here and a vertical here that are perpendicular, right? Those are both on the -2 horizontal. These are both on the 4 vertical. So diagonals are perpendicular. That's interesting. Okay, well, that maybe will come in handy later. And look at each of these lengths, right? If we want to find each of these lengths, we went down 3 and we went over 4, yeah, from 4 to 8. And then we went back 4 and down 3 more. And then we went up 3 and back 4. So look what we have. So just by this picture already, we have diagonals are bisecting each other. So for sure this is a parallelogram, right? Just from diagonals bisecting each other. But also diagonals are perpendicular. And so if the diagonals are perpendicular, then it is also a rhombus. First we have to start with parallelogram and then say perpendicular, so rhombus. Or another way is you could just go, oh look, we did Pythagorean theorem, and all these are 3, 4, 5 triangles, so they're all of length 5, 5, 5. So really the only other thing we need to check is, does it form right angles? So is it a rectangle and a square? And so we could just check any two slopes. Or another way to think about it even more directly is, are the diagonals congruent? Is 8 congruent to 6? No, they are not congruent, so not rectangle, square, right? And so it's just a parallelogram and a rhombus in terms of the shapes we've really investigated. All right, let's go. Oh, zoom, come on, zoom. Work, there we go. Find the area of quadrilateral PQRS to the nearest tenth. Okay, well, the way I see this is a triangle here where they're giving us a height, and we could probably figure out this base all the way across here. And then we have this other triangle like this where we have a height and a base. 9 plus 5 is equal to 14. So I see this as two triangles, and we just need to find a height here and a base over there. So let's find some unknown values. Well, I know my Pythagorean triples, and this is a 5, 12, 13. So I know this is a 12 here. And then look at this. This is a 9, 12, 15. It's a 3, 4, 5 triangle where we multiplied by 3. So it's 9, 12, 15. So I know this is a 15. And then if we needed to go further, we can, but we don't have to. So we have a 15 base, 6 height triangle up top. And then we have a 14 by 12 triangle on bottom. And that's how I saw it, as two triangles. You could have absolutely seen it as 1, 2, 3, 4 right triangles. And that's totally okay. We'll get the same answer. But anyways, here we go. So the area is equal to area of triangle plus area of triangle. So 1/2 and a base times height. So 15 times 6 plus 1/2 12 times 14. I'm going to smash the even numbers in half. So we get 15 times 3. That's the 1/2 times 6. Plus, and over here I'll leave the 12 and divide this 14 by half. So that's 7. So then that gives us 45 plus, what's that, 70 and 14, so 84. So that's 120 and 9. So we get the area is 129, exactly. Ooh, look at that. They were trying to be like, find it to the nearest tenth, huh? But it was exactly. Okay, find the area of trapezoid with vertices. So first thing we got to do is figure out which are the bases. Then we got to find the lengths that go with this. So I'm going to zoom in and just do this small right here. Okay. Making sure I got a small pen going. Okay, so -2, 1, 8, 7, -2, okay, 1, 2, 3, 4, 5, 6, 7, 8. So we got 8, 7 up here. We got 6 somewhere over here, 6, -1 like this. And we got 1, -4 like this. And we got -2, whoa. And we got -2, comma 1. All right, so all I have to do is find the slopes here to see which are the base, and then we'll have to use the distance formula. So what I'm going to do is I'm going to go, I went up 6 and over, right? So yeah, up 6 and over 10. And then over here, I went over from 1 to 6. So I went over 5, and I went up 3. And those are the same slope, right? It's just doubled. So I went over 5, up 3, over 5, up 3 for a total of over 10, up 6. So those lines are parallel. They do have the same slope of positive 3/5. So we know it's a trapezoid. So those are our two bases. So I already know the area is equal to 1/2 base 1 plus base 2 times height. I just need to find those values. So I'm going to use Pythagorean theorem and go 3 squared plus 5 squared equals, I don't know, base 1 squared. So that's 9 plus 25 or 34 equals base 1 squared. So base 1 is root 34. Okay, and then base 2 is the same thing but doubled, right? So we have the double this, double that, so we get equals base 2 squared. So we get, this is 36 plus 100 equals base 2 squared. So 136 is base 2 squared. So base 2 squared, or base 2 is square root of 136. Another way to see that is square root 4, square root 34, or 2 root 34. Because if the 5 and the 3 got doubled, then the hypotenuse got doubled too. They're similar triangles. So we get a root 34 and a 2 root 34 as the two bases. All right, now we just need a height. So here's the 2 root 34 for this length and the root 34 for this length. Now this is where it gets tricky. How do you find the height? Well, the height we need is perpendicular to this. So that's a little tricky, right? We got to find what is the distance between two parallel lines, because you're not just saying what is the length from like here to here of a leg, unless it happens to be that luckily it's perpendicular. Let's check if any of them's perpendicular. So this is back, what, 5? Yep. And up 3. Oh my gosh, look at that. They were so nice to us. Is that a right angle? Let's just double check. We went back. Oh no, I wrote that backwards. We went back 3 from 1 to negative 2. So we went minus 3 back. And then we went up from negative 4. So we went up positive 5. So that's a slope of rise over run, or negative 5/3. And sure enough, this slope here is positive 3 over positive 5. And so we have a slope of positive 3/5, which is perpendicular to negative 5/3. So, oh my gosh, they were so nice to us. We didn't have to do a system of equations to see where a perpendicular line we found intersected with the equation of this line. That's a harder, more interesting problem. Instead, because it's a right angle, oh shoot, I erased way too much there. Instead, we can just find this length because it forms a right angle right here. So all we got to do is find the distance there, which we've already done. It's the same 3 and 5, and so we get the same root 34 for that length because we went over 3 and 5, which is the same triangle we just did right there. So now we've got a right trapezoid where these are both right angles, these are parallel. This is root 34, this is root 34, and this is 2 root 34. So going back to our equation then, we get 1/2 root 34 plus 2 root 34, all times a height of root 34. So that's 1/2 3 root 34 times root 34. Well, root 34 times root 34 is 34. So this is 1/2 times 3 times 34. And so the 1/2 times 34 makes it 3 times 17. And that's 30 and 21, or 51. Well, cool problem. That was interesting. We haven't done one like that in a while. Okay. Find the area of a rhombus with perimeter of 100 and one diagonal with length of 48. Okay, well, I know... Oh, no, that's perimeter, not area. Okay, well, let's draw it first. I don't know. Let's do green. All right, so what we got is we got perimeter 100. But there's 4 congruent sides, so we divide that 100 up, and we get that each side is 25. Okay, And then it tells us that one diagonal is of length 48, so it doesn't matter which one in the drawing. But we do know the diagonals bisect each other because it's a parallelogram, and because it's a rhombus, they're perpendicular, so that 48 gets divided into 24 and 24. And I know my Pythagorean triples, so this is a 7, 24, 25 right triangle. Doesn't come up that often, but you could just Pythagorean theorem and get that that's 7 too, which means this is 7 here. So now the area of a rhombus is 1/2 diagonal 1 times diagonal 2. That's the direct shortcut to get it. So it's 1/2 of 14 times the other diagonal is 48. That's the direct way to get it. Or you could just do the area equals 4 times the area of a triangle, because all 4 triangles are congruent. So it's 4 times 1/2 times base times height, and you get the exact same value either way. So I'm going to go ahead and use a calculator for that. So we get 7 times 48, which is 336. Perfect. Okay, let's go to the next one. Find the area of each polygon to the nearest tenth. A regular octagon, perimeter of 96. Well, I know the area is 1/2 apothem times perimeter. So I already know it's 1/2 something times 96. So we're already like a big portion of the way there. All we need to do is find the apothem. So here's a regular octagon. Okay, if we divide 96 by 8, I'm double checking, but I think that's 12, right? Yep. So we get each of these sides is 12. Well, the big idea here is from the center of a regular polygon, this is an isosceles triangle. We can find the angle in the middle by saying there were 360 degrees, but we divide the 360 into 8 equal parts and get each of these is 45 degrees. So that's enough information now to use trig to solve it. So we have a big isosceles triangle like this, the 12 and a 45, cut it in half, and we get 22.5 and 6, and we're looking for this apothem. So we go, oh, well, that means the tangent of 22.5 equals that 6 over the apothem. So multiplying by a and dividing by tangent, we get the apothem is 6 divided by the tangent of 22.5. All right, so then we go back over here and we go 6 divided by tangent of 22.5. All right, so now this is equal to, so if we did it exact, it would be what? 6 times 96 divided by 2. So it would be 288 over the tangent of 22.5. That's the exact answer. But if we wanted to approximate it to the nearest tenth, we would go that divided by the tangent of 22.5 is about 695, and it would be 0.29 ... but 29 will round to 3. So that's approximately what we get. All right, a regular pentagon with apothem of 5. So again, we have the area is 1/2 a times p, so the area is 1/2, and then the apothem is 5, and all we need to do is find the perimeter, or just really we're looking for a single side length. So off to the side, we have the same thing here. We have a regular pentagon. Okay, we know that the apothem is 5, so right here is 5, and we have all these isosceles triangles we can cut it up into. We have 360 degrees that we divided by 5, so we know this whole angle was 72. But then we divide it in half, and we get each of these smaller angles is 36. And really we need the perimeter or just a single side length. And so we're really looking for x here. And so we go, okay, so we have that I'm under the wrong problem if I write up there. So I'll write in the shape, okay? So we have the tangent of 36 equals x over 5. And so that multiplying by 5, we get that x, or that half side length, is equal to 5 tangent of 36. So in other words, a single side length is double that, or 10 times tangent of 36. There's 5 of those, So the whole perimeter is 5 of those 10 tangents. So 5 times 10, we get this is 50 times tangent of 36. And so if we multiply that, we get that that's exactly equal to 125 times the tangent of 36 degrees, or that's approximately, so 125 times tangent of 36 degrees, that's 90.817 yada yada, but 81 rounds to 90.8. Okay, a regular nonagon with side length of 12. So regular nonagon, so we have 9 sides, so draw it, that's my regular nonagon. So a single side length is 12, and we're just doing the same thing here. So this time, let's do it different. Instead of using the formula, let's just find the area of a triangle and multiply it, okay? So we have 360 degrees divided by 9 for the nonagon. So each of these is 40 degrees. All right, and now that's enough. So all we got to do is find the height. So if I cut that triangle in half, I get 20 degrees and right angle and 6. And so I know that the height of this would be tangent of 20 equals 6 over the height. So multiplying by h, dividing by tangent, we get the height is 6 divided by the tangent of 20. Okay, that's the height. And so the area of one triangle is equal to 1/2 the whole base, which is 12, times the height. And so when I'm talking about one triangle, I mean one isosceles triangle, not the right triangle that we cut in half version. Okay, and then the height was 6 over tangent of 20. Okay, so we could simplify that to be 1/2 of 12 is 6. 6 times 6, so this is 36 over tangent of 20. That's the area of one of those isosceles triangles, but there's 9 of them. So the area of the nona is equal to 9 times 36 over the tangent of 20. And 9 times 36, what is 9 times 36? That's 324. So we have the area is 324 over the tangent of 20, or we're plugging that in. That's 890 point, and it would be 1/8, but we can round that to 0.2. All right, let's keep going. So find the area of the shaded region to the nearest tenth. Assume the triangle is equiangular, and this is the same thing as saying equilateral. Okay, so it's giving us that the radius is 7. Well, I know the area total overall is equal to the area of the circle minus the area of the triangle. So pi r squared minus 1/2 base times height. You could absolutely use regular polygon 1/2 apothem times perimeter, but that seems like overkill for a regular triangle. You just do 1/2 base times height. Well, we know that the radius is 7, so we have it's pi 7 squared minus, and we don't have the base or the height. So we need to find the base and we need to find the height. So let's draw our little shape here. I'm looking for some room. Let's do it up here and just zoom in. All right, so in a regular triangle, we have 60, 60, 60. We have this drawn to the center. Now, if we cut straight down the middle, that cuts this into 30 and 30 and 90. And that cuts that 60 into 30 and 60, right? So now we have a 30, 69 triangle. So that's 7. So that's similar to a 60, 30 triangle that's 1, √3, and 2. So I don't have an easy multiple to get from 2 to 7. Now you really do. You just multiply by 7 over 2. But let's pretend we don't have an easy multiple, and we're looking for x. So we'd say going, let's go this direction. So x is on top, doesn't matter. But x is to √3 as 7 is to 2. And then we cross multiply and we get 2x equals 7 √3. So x equals 7 √3 over 2. Okay, so that's half of the height here, or half of the base. And so then the whole base would be 2 of those. So the whole base would be 7 √3, right? That's just 2 of those, because multiplying by 2 gets rid of So 1/2 base times height down here, the base is 7 root 3. All right, well, let's investigate this shape further. Well, this 60 here cut this into 30 and 30. So this is isosceles. So this was a 7 right here. And then what's this length right here? Well, let's look at our triangle. Again, it's similar here in that this is a 1. Oh my gosh, I used the eraser. This is a 1 to 2. In other words, this is a 1 to 2. So this is a 7/2 right there. All right, or you could use proportions to set that up. So the entire height there is 7 plus 7/2, or in other words, 14/2 plus 7/2, or 21/2. So the whole height is 21/2. Another way to do that is once you got this as that bottom leg, you could say, well, half of the big triangle is a 60/30, right? Where this was 7 root 3 over 2. And we're looking for this height, and we could say, well, that's in a ratio of 1 to root 3 to 2 in our triangle. So we just multiply it by root 3. And what is off to the side? 7 root 3 over 2 times root 3. Well, that's just 7 times root 3 over 2, or 21 over 2. So you could have done it more directly that way. Doesn't matter which way you do it. So anyways, back to the overall area. We get that 49 pi for the circle minus, and then we just have to clean this up a little bit. Well, top times top and bottom times bottom. We get a fourths on the bottom. And then on top, we get 21 times 7 root 3, which is just 21 times 7, or 147 root 3. And we can't simplify that anymore. It just says find the area, so it didn't tell us to round it, so I'm going to leave it like that. 49 pi minus 147 root 3 all over 4. Okay, so find the area of each of these, okay? Well, for the first one, I'm going to say this is an area of a trapezoid minus the area of a half a circle. That's how I'm going to see this problem. And we don't know the height. That's all we're missing here. So we got to find this height. Okay, so can we do it? Well, look at this. We have to assume these are right angles, okay? And so we got this rectangle. So that means this is 6 down on the bottom, which means we're left over with a 3. So we have a right triangle with a hypotenuse of 5 and a leg of 3. That means we have this side here is a 4, which means this is a 4, which means the radius is 2. Done. So we get, okay, we have the area of a trapezoid, 1/2, base 1 plus base 2 times height, minus the area, half the area of a circle, or 1/2 pi radius squared. So we get, what, 1/2 of 15 times 4. That's 1/2 of 60. Or in other words, that's 30 minus. And then this is 1/2 of 4 pi. Or in other words, a 2 pi. So this is 30 minus 2 pi. Cool. Okay. Now let's do... again, we're just doing an area. Yep, okay. And then this one here, we're going, okay, well, what's this? This is, I would definitely do this as 3 separate shapes. So cut it here, cut it here. So we have a radius 1.5. That's going to be just a little annoying with decimals in this problem. Here we subtract the radius of 1.5, and we get this is 5 long for this rectangle. And then up here we have a 5 and a 5.5, so we just have to do Pythagorean theorem to get this side. So we go, okay, well, 5 squared plus b squared equals 5.5 squared. And then you just do a bunch of, so that's that. I'm going to do that on a calculator. So 5.5 squared, whoops, I pressed the wrong button. 5.5 squared minus 5 squared is, so that's then b squared equals, well, that's not a lot, equals 5.25. Okay, so b is the square root of 5.25. Does that have a nice square root? I don't think so. No, it doesn't. Well, because what is that? That's 26 fifths, right? 26 fifths. Yeah, that doesn't have a nice square root. Anyways, so that's what b is over here. So that's the square root of 5.25. And now we just have 3 separate areas. So let's do it in blue. So we have area of, what? It didn't switch colors to blue. Oh, I can't switch colors to blue. Oh, it's because my iPad's melting. There we go. I'm back. Okay, so we have the area of this half circle plus the area of rectangle plus the area of triangle. So this is 1/2 pi r squared plus base times height plus, this is a different 1/2 base times height. I know I'm using the same letters there. Okay, so this is 1/2 pi 1.5 squared plus 5 times 3 plus 1/2 5 times square root of 5.25. This is crazy. So 1.5 squared is 2.25 divided by 2. So we get, this is 1.125 pi plus 15 plus 5 root 5.25 over 2. There we go. That's as crazy as the answer gets. Okay, well, let's do that. So times, and I'm just going to arithmetic this thing out. So that's approximately 24.262 ... or 24.3. Crazy decimals in that problem. And then what about this one? So they give us on a coordinate plane for number 4. Well, we could just chop that into a triangle and chop that into a rectangle. Not even a rectangle, square. So we have 3 by 3. We have, this is a radius of 1.5. And then we have this triangle which has a height of 3 and a total base of 1, 2, 3, 4, 5, 6, 7. Okay, so it's really similar to the last one. It's the same shapes. So we have the area of a half a circle plus the area of a square rectangle plus the area of that triangle. So that's 1/2 pi r squared. It's the same 1/2 pi r squared plus base times height plus 1/2 base times height. The numbers just work out easier in this one. So in this one, we have that same 1/2 as the radius. So this is 1.125 pi as the area of that half circle. And then plus 3 times 3 is 9 for the area of the rectangle. Plus 1/2 of 3 times 7 is 21. And so we get, what, 9 plus 21 halves. So that's 18 halves plus 21 halves. So that's 39 halves. So we get 1.125 pi plus 39 halves. Crazy problems. Okay, to win a certain board game, a tossed token must land on a shaded square on the board. The probability of winning is 23%. If the board is a total of 130 congruent squares, how many of these are shaded? Well, that means we have 23% of the total 130, how many of them? So out of 130, how many make 23%? And that was only approximately, right? So it's saying it wasn't exactly 23, they rounded. So if we cross multiply, we get 100x equals 23 times 130, and then we divide by 100. So x equals 23 times 130 all over 100. So 23 times 130 divided by 100 is about 29.9. But since they were approximate, that means there was 30 squares was the answer there, okay? For questions 16 and 17, round to the nearest. So these ones aren't, we didn't do probability in right now, but I'll still solve them. What's the probability that point lands in the shaded regions? Okay. Oh, no, sorry. In the shaded sector. Okay, so sector is this shape right here. And then the other question says, what if it lies in the shaded segment? So segment is this separate one. So there's two separate things. There's a segment and there's a sector shown in this. So these are two separate questions. So let's do it. All right, so we need the radius of this circle. It tells us the diameter is 6. That means the radius is 3. Well, the area of the sector is just, it's a fraction of a circle. So how many degrees out of 360? And then times the area of the whole circle, because the whole circle has a pi r squared or a pi 3 squared. So it's just saying what fraction of the circle, right? Like how much pi did you cut in that slice? And so we just got to figure this out. Well, this goes through the center, so it's 180. That means the leftover here is 40 degrees because we had 40 up top. So that means we have 40 degrees of this. So that's equal to 1/9 1/9 times pi 9. Or in other words, we have the area is exactly equal to a pi. So it's saying what's the probability that a point selected at random lies in the shaded sector. So I'm assuming they mean that a point selected at random from in the circle, right? Because we have to know what the outer limit of possibilities are. But the shaded region has an area of pi. The question is, what is that out of, right? We're saying, okay, well, we have pi area out of what total? So if it's out of the circle, then we would say the probability is our area of pi out of the entire circle, which is pi 3 squared. Or in other words, it's pi out of 9 pi. Or in other words, it's 1/9 of the time, which we could have gotten right here. The sector is 1/9 of the circle. And so it just depends. But they could have said out of this square, what's the probability? Or whatever they were doing. Right? So here, assuming they meant out of the circle, probability is 1/9. What's the probability that a point selected at random lies in the shaded segment? So what we have to do here is we go, okay, first we got to find this sector. So this is a 100-degree sector. Okay, so we go, okay, well, the area of the sector is 100 out of 360 times pi 3 squared. Okay, but then we got to take away the area of the triangle. Okay, that's what we got to do. So we have to look at this triangle. Well, we know this triangle off to the side here is isosceles because we have radius of 3, and a 100-degree wedge. So we cut it in half and we get a 50-degree and a right angle and a 40-degree. And so all we need to do is find the height, and this is half the base, so I'll just call it x. Okay, well, sine of 40 equals h over 3. So the height is 3 times sine of 40. And for x, we go the cosine of 40 equals x over 3. So x equals 3 times cosine of 40. So that means the whole base is twice that, or 6 times cosine of 40, all the way across the base of this triangle. So when we go to take the area of this triangle, I'm going to erase area of triangle here and say this is 1/2. And then the base of the triangle is 6 cosine of 40. And then times the height of the triangle, which is 3 sine of 40. Okay, and the 1/2 and the 6 cancel to make a 3. So the exact answer here for the actual area of that region would be, and we could simplify this a little bit to be 10 out of 36, which then the 9 and the 9 cancel. And that leaves you with a 4. So we have 10/4 of pi, or 5/2 of pi, minus, and then we have 3 cosine 40 times 3 sine of 40, or 9 sine of 40 times cosine of 40. I don't know why I wrote the sine first, doesn't matter. So that was the area of the, I wrote area of sector, but we actually did area of the segment because I ended up taking away the triangle. Okay, so that's the area. And then we just say, well, that's out of, so we find that decimal value, and then we go, that's out of a total of pi r squared. Or in other words, out of the total possibility of 9 pi, what did we get? So let's just approximate that really quick. We get 5 divided by 2, or 2.5 times pi. Okay, and then we're going to go subtract 9 times the sine of 40, end those parentheses, times the cosine of 40, end those parentheses. So this is approximately equal to 3 point. I'm going to keep a lot of decimals because I'm still in the middle of a problem. So I'm going to write all these decimals, okay? And then we need to say, well, out of 9 pi, what probability is that? So if we divide that by, and I'm going to go in parentheses, 9 times pi, or about 27, we should get about 1 in 9, give or take, and we get a probability of 0.121. Now notice that 1/9, that was, well, it's not exactly, I mean, that's equal to exactly 11.1 repeating percent. And the area here is 0.12104 ... or about equal to 12.1%. So pretty close in actual probability in landing in the 2, because we had wider but the triangle removed, or narrower, triangle not removed. Okay, last problem. Find the area of the shaded region to the nearest tenth. Assume the hexagon is regular. So this isn't that crazy. I don't know how this is a bonus problem. So the area is simply the area of the circle minus the area of the whatever-agon, right? And it's saying that it's regular. And so we just go pi r squared. We don't have the radius yet, but pi r squared times 1 minus the apothem times the perimeter. So all we got to do is go, oh yeah, and in a regular hexagon, that's when we do 360 divided by 6. We get 60. And we go, oh yeah, this is the equilateral 60, 60, 60. So we know the radius of the circle is 8. So that's already pi 8 squared minus 1/2. We need to find the apothem, and the perimeter is just 6 times 8 is 48. So really all we're looking for is the apothem here, and that's not so bad, because we just go, we have an equilateral triangle, which is 8, 8. We cut it in half, and the bottom 8 gets split into 4 and 4. And then we could use Pythagorean theorem, or remember that splitting 60 into half is 30, and we have base of 60. So that's similar to, let's do it this way, similar to 30, 60, 90, or 1 root 3 and 2. And so that was just a simple multiply by 4 copy. So the height would be 4 root 3. So we go back over here and go, the apothem is just 4 root 3. And so this ends up being, the area is 64 pi minus, and then we can just do some arithmetic here and go, half of 4 times 48 is 96 root 3. And that would be the area. And then you could always round it to whatever you wanted. So 64 pi minus 96 root 3. All right, guys. Hope you enjoyed that. 2 more chapters to go.